So here the next part of the discussion, that is we are going to start P block elements, that is 15 group elements. So here if you go to the 15 group elements, these 15 group elements, they are also called 15 group elements, also called nicogens. They are also called nicogens, or you can say nitrogen family, because the starting element is nitrogen. That's why we can call it as nitrogen family. So here can be called as nitrogen family. And if you go for the elements, so here if you go to the elements of 15 group or nitrogen family, if you take elements, the symbol of nitrogen is N, the first element is N, its atomic number is 7, and its electronic configuration, let us write the nearest noble gas configuration, that is helium of 2s2 2p3 is the nearest noble gas configuration of nitrogen. And in the electronic configuration you are finding that the last 5 valence electrons are entering into, that is 2s orbital and 2p orbital. If you go to the phosphorus next element, for 7 you add 8, so it is going to become 15. So this is neon of 3s2 3p3 is the electronic configuration. Again the last 5 valence electrons are entering into the 3s and 3p orbital. The nitrogen, phosphorus, arsenic for 15 you add 18, this is going to become 33. So 33 is the atomic number of arsenic. As stands for arsenic, and here this is going to become argon of, that is 3d10 of 4s2 of 4p3 is the configuration. So this is 10 electrons, 2 electrons and 3 electrons. Argon 18 electrons are there, 18 plus 10 28, 28 plus 2 30, 33 is the configuration, total number of electrons are there. Then antimony, if you take for 18 again you add, for 33 again you add 18, so this is going to become 51 is the atomic number of antimony. Sb stands for antimony Latin name is TBM, so therefore Sb is the antimony. So this is going to become krypton of, that is 4d10 of 5s2 of 5p3, then nitrogen, phosphorus, arsenic, antimony and bismuth. If you take, so add 32 here, 32 means 80, bismuth is 83 atomic number, so this is going to become xenon of 4f14 5d10, then 6s2 of 6p3. So it's very clear that here the 4f14, that is xenon atomic number is 54 electrons plus 14, 54 electrons plus 14 is 68 plus 10 78 plus 2 70, and 54 plus 14 68 plus 10 78, 80 and 83 is the total number of electrons present in, that is the bismuth. So fine, this is the general electronic configuration of the 5th A group family, and the last 5 electrons are entering into the 5s, that is 5s and 5p of antimony and 6s and 6p of the bismuth. So therefore from this we can give a conclusion. We can say that the general electronic configuration, therefore the general electronic configuration of the 5th A group family is ns2np3. So what we can notice here is, like if you go to the general electronic configuration, from the general electronic configuration, it is very clear that based on general electronic configuration, that is ns2np3. So in the ground state, suppose if I am taking the ground state, it is having ns orbital, that is ns2 np3, and this is nd0. So if you go for ns orbital, it has one sublevel, and ns orbital has one sublevel and one orbital, np sublevel has 3 orbitals, and nd has, that is 1 2 3 4 5 orbitals. So this is nd0, this is np3. np3 means it has 3 electrons, and this is ns2 means it has 2 electrons. One is clockwise and the other one is anti-clockwise. As of now, because of the 3 unpaired electrons present in the np orbital, yes, right now it can these 5th A group family elements, because of the 3 unpaired electrons present in the NP orbital, its oxidation state, we can take OS stands for oxidation state. Oxidation state is equal to plus 3 oxidation state. It can exhibit a plus 3 oxidation state. The best example which can show plus 3 oxidation state is, that is, you can take you can take, that is N2O3, you can take as the best oxidation state element. Nitrogen can show plus 3 oxidation state, and you can take even PCl3 also. PCl3 also will show plus 3 oxidation state, also can show plus 3 oxidation state. So this is in the ground state. So now from the ground state you can promote one of the electron from NS orbital to, you can promote its electron to Nd. So under such circumstances you are going to get excited state 1 configuration. This is NS1. So I am just cutting off this now. NS1, this is going to become NP3, and this is going to become ND1 under such circumstances. So this is NS1, this is NP, there are 3 electrons here, and this is ND, 1, 2, 3, 4. So total 5 unpaired electrons are there in the first excited state. So it is very clear that this is ND1, this is NP3, and this is NS. So therefore here you can say that the oxidation state is plus 5, and the example for the plus 5 oxidation state is, we can take N2O5. In N2O5 nitrogen has plus 5 oxidation state, and even PCl5 also, phosphorus pentachloride also, it has plus 5 oxidation states. So this is the maximum oxidation state where the nitrogen family can show its oxidation state. However, that is, so therefore I can come to one conclusion: the lowest possible oxidation state, lowest possible oxidation state, if you take, it is -3, and the highest possible oxidation state and the highest possible oxidation state, it is plus 5. The lowest oxidation state is because of the lowest possible oxidation state is because of the orbitals NS and NP orbitals are responsible for the lowest oxidation state oxidation, and the highest oxidation state is because of the NS, NP, and also ND, that is N-1 of D, because NS and NP. Okay, here I am going to take this as ND or N-1 of D. So here ND orbitals, all 3 are responsible for the highest oxidation state. Fine, whatever may be the case, here you find that now we can also speak about the stability of the oxidation state. That is, if you go for the stability of the oxidation state, if you speak, you find that in general the common oxidation state for any element in the group families, it is always equal to its group number, because these elements belongs to the 5th group, 15th group, 50th group. That's why the common oxidation state, I can say that it is plus 5. But plus 5 oxidation state, the stability of the oxidation states, you find that the stability of, that is plus 5 oxidation state, let me put it in this way: plus 5 oxidation state stability decreases, from nitrogen to bismuth, and plus that is, if you go for bismuth, this bismuth is having an exceptional property. If you go for bismuth, this shows an important property called inert pair effect. This bismuth shows an important property called inert pair effect. So when it is showing inert pair effect, you know that what is the meaning of inert pair effect. The reluctance of NS orbital electrons to participate in the bond formation can be termed as inert pair effect. I repeat, here the bismuth shows the inert pair effect, and if you go to the term this inert pair effect, it means that the reluctance of the NS orbital electrons to participate in the bond formation, we can call them as inert pair effect. So bismuth, what it is going to do is, it is going to lose these 3 electrons efficiently, but it is not going to lose the electrons which are present in the NS orbital. So the inability of the element to lose the electrons from the NS orbital, but whereas it can easily lose electrons from the NP orbital, can be termed as inert pair effect. So surprisingly, when you go for bismuth, instead of showing plus 5 oxidation state, it is more stable because of inert pair effect. It is more stable in plus 3 oxidation state, but bismuth is not stable. It is not stable when it is in plus 5 oxidation state. The reason is because again of the inert pair effect. So that's the reason we can say plus 3 oxygen state as we move from that is nitrogen to bismuth, it will increase. So this is one reason we can say that why the oxidation state of plus 3 increases from nitrogen to bismuth, and why the oxidation state of plus 5 decreases from nitrogen to bismuth. Why it decreases from nitrogen to bismuth plus 5 oxygen state, and why it increases from nitrogen to bismuth of plus 3 oxygen state is again dependent upon the inert pair effect in the nitrogen family. So if you go to the physical properties, physical properties of nicogens, what we can notice here is like go for nitrogen, phosphorus, arsenic, antimony and bismuth. So nitrogen is a non-metal gas, gaseous element. Phosphorus, actually nitrogen and phosphorus, both of them are non-metals, but this is non-metal solid. And here these you can take arsenic and antimony, these are metalloids and metalloid solids. And if you take bismuth is distinctly a metal, and it is monoatomic. And of course arsenic and antimony, they can be tetraatomic, and even phosphorus also, it is tetraatomic, and nitrogen is a diatomic in nature. So that means because we are speaking about their atomicity and their nature, I can say that nitrogen, if you take nitrogen in the atmosphere, if you go for the nitrogen particularly, it occupies 78% of volume in atmosphere, and this nitrogen is available in different mineral ore forms. The sources of nitrogen is available in the form of KNO3. This is KNO3, then Indian saltpeter, and if you go for NaNO3, child saltpeter, and this nitrogen is also available in the form of proteins and amino acids in various sources. And the pure nitrogen can be obtained by fractional distillation of liquid air. Pure nitrogen can be obtained by fractional distillation. FD stands for fractional distillation of liquid air. It can be obtained, or you can also prepare this nitrogen, that is you can take barium azide. If you take N3H, so this is barium azide. On heating, this is barium azide. Upon heating also you can get the pure nitrogen, that is barium, can be obtained. And here you have 6 nitrogens, so take 3 here. So this barium is a solid. In this way also we can obtain the nitrogen in its pure form. And if you go for phosphorus, if you are going for phosphorus, this phosphorus is available in the form of, that is phosphates. It is available in the form of phosphates. When you say phosphates, you can take, it's available in the form of fluorapatites. It's available in the form of apatites. Apatites is a mineral ore which contains 3Ca3PO4 taken twice of 3CaX2. So in the place of X, if you can substitute fluorine and chlorine, for example, fluorine, chlorine and bromine you can substitute. But if you want to get fluorapatite, then suppose if you want the composition for fluorapatite, then you can use the formula fluorapatite apatite, you can use the formula, that is 3Ca3PO4 taken twice of 3CaF2. This is fluorapatite. And if you want to use the chlorapatite, apatite, we can use the formula, that is 3Ca3PO4 taken twice of 3CaCl2. And it is also present in animal. It's a source of lipids, proteins, and in bones. For example, in bones, this phosphorus is available in the form of phosphates. When it is phosphates, you can say that it is Ca3PO4 taken twice, which we call it as calcium phosphate. So this is bone ash. You can call it as bone ash or Thomas slag. Metallurgical name is Thomas slag. So all this you can take, and you can also take, similarly you can find the arsenic and antimony also. They are available in the different mineral ore forms, and bismuth also, it is available in the form of different mineral ore forms. So if you go to the next part of the physical properties, you can just add one point here saying that is second one, that is ionization enthalpy. If you take ionization enthalpy, if you speak about the ionization enthalpy, because we know that the general electronic configuration of the 15th group, that is nicogens, is already ns2np3. That means it's very clear that here they have half-filled stable, that is half-filled stable electronic configuration we are able to observe. Then because of the half-filled stable electronic configuration, usually the amount of energy, the amount of ionization enthalpy to remove the electron requires large amount of energy. And you know very well that ionization potential or ionization energy, always it is inversely proportional to the atomic radius. It is inversely proportional to atomic radius and stable electronic configuration. So I can say that in the ionization enthalpy decreases from nitrogen to, that is bismuth. So therefore the decreasing order, nitrogen is greater than phosphorus, is greater than arsenic, is greater than antimony, is greater than bismuth. This is ionization enthalpy. Then if you go for, that is electron gain enthalpy, that is electron gain. If you go for electron gain enthalpy, is nothing but electron affinity. Usually I can say that all these 50th group family elements, they have very low electron gain enthalpy. That is almost because very low electron gain enthalpy is observed because they have half-filled electronic configuration. Since they have half-filled electronic configuration, neither they can lose the electrons, neither they can gain the electrons. So they have very low electron gain enthalpy. But however, if you go to the decreasing order, for this decreasing order, if you take the electron gain enthalpy decreasing order, so decreasing order of electron gain enthalpy, if you take for this nicogens, you can take phosphorus is greater than nitrogen, is greater than arsenic, is greater than antimony, is greater than bismuth. So that's because here less electron repulsions are there, here more electron repulsions are there. You can take the electron gain enthalpy. And next is, you can add one more, that is anomalous behavior. This is very important point. Anomalous behavior of the nitrogen molecule. Why? What are the reasons for the nitrogen molecule to show anomalous behavior? The first reason is it is atomic size, smaller atomic size, point number one. Second is it's a triple bonded molecule. It has high bond enthalpy. It has very high bond enthalpy, that is because almost I can say it is nitrogen triple bond. Very large amount of energy is required to break this nitrogen triple bond, where it is equivalent to nearly 946.5 kilojoules per mole of energy is required to break the nitrogen triple bond, and it has very high electronegativity. It has high electronegativity. It can readily form multiple bonds. It can readily form multiple bonds of the type p pi overlapping, because of the effective overlapping of the smaller size will allow the orbitals to overlap effectively, and it results in the formation of the triple bonded molecule. That is, if you take nitrogen molecule, you can find that each nitrogen molecule is having suppose if I am taking the first nitrogen molecule, this is px orbital, px, and this is second, again we have a px, and this is third, again we have a py and pz. This is a first nitrogen molecule, and if you go for the second nitrogen molecule, of course we have each pure atomic orbital of the nitrogen. Because of this half-filled electronic configuration, we can just take, that is electron px orbital, this is py orbital with an electron, and again pz orbital. So if you go for pz, this is the pz orbital, so therefore I can say that px to px, and this is py to py. So here one more overlapping is taking place. So this is pz, so pz to pz. So here we have one pi bond, here we have one pi bond, and here we have one sigma bond. Lateral, that is sidewise overlapping, the overlapping taking place along the internuclear axis results in the formation of sigma bond. Rest of the two overlappings because of the pure p atomic orbitals, that is the lateral overlapping is taking place. That's why we can say that in the nitrogen molecule, between two nitrogen atoms, you can find that there is a triple bond, and the middle one is sigma, the upper and the below one you can take it as, that is pi bond. So we have one sigma bond and two pi bonds also will contribute for the stability of the nitrogen molecule, and this also contributes for the anomalous behavior of the nitrogen molecule. So these are some of the interesting points where we have to keep it in mind, why the nitrogen molecule can show the anomalous behavior. So suppose here if you are taking one question, why NCl3 exists but NCl5 do not exist, is one question where we can answer. That's because in NCl3 exists because here the bonding is between N and S and P orbitals. That is, the answer for this is, the simple answer for this is, nitrogen do not have d orbital in the excited state, because nitrogen maximum number of electrons we can take here due to the absence, we can simply say due to the absence of d orbital and smaller size is one reason why NCl3 can exist but NCl5 do not exist. And you can also add one more point here, but PCl5 molecule exists. It is again because in phosphorus, due to availability, due to large atomic size and utilization of d orbital electrons in the excited state, phosphorus can exist in PCl5 form. This is one question where we can answer. And another one is, if you go for what is the maximum covalence, that is maximum covalency of nitrogen and phosphorus is, that is, if you go for nitrogen has a maximum covalency maximum covalency. You can understand the concept of covalency by simply using some shortcut format, that is the maximum number of covalent bonds in a given compound surrounding a given element can be called as the covalency. So the maximum covalency of nitrogen is up to 4. You can take the best example of the maximum covalency in nitrogen is ammonium cation. If you go for ammonium cation, it has 4 covalent bonds like this: hydrogen, hydrogen, hydrogen and hydrogen. We have 4 hydrogens. So here one positive charge. So it is surrounded by 4 covalent bonds. So therefore the covalency is 4. But if you go for phosphorus, maximum covalency is up to 5. The reason is because you can take maximum covalency is up to 6. For example, if you take, that is, it can exist in the form of suppose you take PCl5 molecule. When it dimerizes, it becomes P2Cl10. When it is P2Cl10, it becomes a solid. And this decomposes to give 2 species. One is PCl4 plus and the other one is PCl6 minus. In PCl4 plus, the maximum covalency is 4, and here the maximum covalency is equal to 6 in the case of PCl6 minus. That means phosphorus pentachloride is trying to dimerize. When it is dimerized, you get P2Cl10, and these are in the 2 monomeric forms. So in this way you can understand. And what is happening here is the maximum covalency of nitrogen is only up to 4. It is the low covalency, that is the lowest covalency in nitrogen is because of 2 reasons. One is it has weak nitrogen to nitrogen single bond, and another reason is greater electron repulsions between bonding and non-bonding electrons. Greater electron repulsions between the bonding and non-bonding electrons. The maximum covalency of nitrogen is restricted only up to 4. But if you go for phosphorus, for example, this phosphorus, it is showing the maximum covalency up to 6 because it is available in the form of, that is, trialkyl. If you take trialkyl phosphoxide, you can take trialkyl ylides, that is CH2. If you take, this is phosphorus ylide, this compound we can call it as ylide compound. Call this as ylides. So during the ylides, they behave as, here they are behaving as ligands. Here they behave as ligands, and when they are behaving as ligands, then you find that they have triethyl phosphorus. In the place of alkyl group, you can take triethyl phosphorus. Once they behave ligands, their covalency exceeds up to beyond 4 and it reaches up to 6. So 6 is the maximum covalency for phosphorus and 4 is the maximum covalency for nitrogen, and these are some of the variable points where we need to understand and make a comparison. So if we go to the chemical properties, physical properties are completed. Now we will go for chemical properties. In chemical properties, we can take, that is the first one, that is hydrides. If you go for hydrides, all the hydrates are of the type, they form hydrates of the type MH3. So here if you take MH3, you can take NH3, you can take PH3, and you can take, that is ASH3, SBH3 and BiH3. So that means we have the hydrates under the name, that is ammonia, NH3 is ammonia, PH3 phosphine, ASH3 arsine, and SBH3 is stibine, and BiH3 is bismuthine. So here what we need to understand here is, suppose if you take the trends, that is periodic trends of hydrides. If you take periodic trends of hydrates, if you take, particularly in terms of, that is melting point, and boiling point. Particularly if you take the boiling point of hydrates, if you take, usually boiling point is directly proportional to hydrogen bonding and directly proportional to molecular weight. But in general, because ammonia molecule is having hydrogen bonding, so what we are going to do is, like, increase in the boiling point increases with the increase in the size of the molecular weight of the hydride. So if you go to the increasing order, you can take, that is, here one important point what we can note down here is, ammonia is an associated liquid because it has intermolecular hydrogen bonding. It has intermolecular hydrogen bonding. So what we are going to find here is, like, if you are taking the trends like this, if I am going to take the graph for the boiling point of the hydrides, particularly you take the temperature, nature of hydride, you take the nature of hydrides on x-axis and their respective boiling points. So here you find ammonia, then you find, that is, phosphine and arsenic. But from arsenic suddenly you find that antimony and bismuth, you find sudden rise in their, that is, boiling point. So the graph looks like this, it goes in this pattern like this. So based on this, what we can notice here is, something you are going to, first three hydrates, there you find that there is a decrease in the melting point and boiling point. Next three hydrates there is increase. So therefore there is an irregular trend which is observed in the case of the boiling point. So here if you look into the graph and if you are going to study the increasing order of boiling point, you find that this is the kind of variation taking place from one hydrate to another hydrate. First ammonia, next phosphine. From ammonia to arsine, you find that there is a gradual decrease in the boiling point, but suddenly the boiling point increases from that is stibine to bismuthine. So if that is the case, this is the order you can notice. First you get the bismuthine has the highest boiling point based on the molecular weight, then antimony also it has higher boiling point, but ammonia, because it is a associated liquid, it tries to overthrow the boiling point of the arsine and the phosphine. So that's why phosphine is kept in the last and bismuthine is kept in the first, but the ammonia occupies the middle position in terms of boiling point. But however, if you go for melting point, ammonia has more melting point than going back to stibine, then going back to arsine, and then going back to phosphine. And bismuthine, because of its large size of the metal, we are trying to ignore it. And if you go for increasing order of thermal stability, yes, here there is no deviation, it follows the regular trend. Ammonia has more thermal stability than phosphine, has more thermal stability than arsine, has more thermal stability than antimony, that is stibine, has more stability than bismuthine. So the reason here is why the thermal stability is increasing from, that is, bismuth to nitrogen in their respective hydrates, is because of the element hydrogen bond energy, that is MH bond energy, element bond energy increases, hydrogen bond energy increases. So this M is the element here, and element hydrogen bond energy increases. M can be anything, nitrogen, phosphorus, arsenic, antimony, bismuth increases. And if you go to the reducing power, if you go into the increasing order of reducing power, if you take, yes, reducing power always depends upon the increase in the metallic character. So just reverse this order. So you get bismuthine has the highest reducing power compared to that is stibine has the most reducing power compared to arsine has the most reducing power compared to phosphine has the most reducing power than the ammonia. So this is the point which you have to keep it in mind. Of course, in all the cases the central atom occupies with one lone pair of electron. So the next part of the discussion is, that is, oxides of nitrogen and phosphorus, oxides of nitrogen and phosphorus. If you take oxides of nitrogen here, if you are going to take oxides of nitrogen, if you are going to take, so here we have that is 5 important oxides are there. One is that is nitric oxide, then nitrous oxide, then you have nitrogen dioxide, then N2O3 and N2O5. These are the different oxides and their respective names, that is name of the oxide. I can just put it like this. This is oxides, then go for name of the oxides, name of oxides, name of the oxides. If you take this is name of the oxides, then oxidation state of the oxides. If you take this, if you create these 3 columns, yes, first one is nitric oxide, this is nitric oxide, it is neutral and paramagnetic in nature, and it is colorless, this nitric oxide. Its oxidation state is that is +2. Go for nitrous oxide, it is very popular. We can call this nitrous oxide as laughing gas or nitrous oxide. And here if you take, yes, this is also neutral, it is a neutral oxide, and it is colorless. And of course its oxidation state is +1. Then go for nitrogen dioxide. It is the only oxide which is acidic oxide. It is acidic oxide. It is colored reddish brown. Then it's odd electron. It has an odd electron nature and it is paramagnetic. If you go for N2O5, it is also acidic oxide. It can be called as sesqui. You can give a special name. This is called sesqui oxide. This is a sesqui oxide and it is bluish liquid. And yes, it forms a mixed anhydride. It can form a mixed anhydride, and of course, yeah, here the oxidation state is +4 and here again the oxidation state is +3. And the last one is nitrogen pentoxide. This is highly acidic oxide and it is colorless. So these are some of the important characteristic features and it is +5 oxidation state. So what is interesting here is, among these oxides, what is interesting here is, like if you go to the structural aspects of all these oxides, that is first one, if you are going for first one, that is nitric oxide, NO. If you take, it can be prepared by taking ammonia gas when treated with oxygen in the presence of platinum or vanadium pentoxide catalyst at around 300 to 300 degrees centigrade to 500 degrees centigrade. It gives nitric oxide gas plus H2O liquid. You can balance the equation, take 2 over here and take 3 over here and take 2 over here. The reaction is going to get balanced. So if you go to the nitric oxide structure of, if you are going back to the structure of nitric oxide, what we are noticing here is, like nitrogen, number of valence electrons are 5 valence electrons, and oxygen 6 valence electrons. Nitrogen has 5 valence electrons and oxygen has 6 valence electrons. So total we get 11 electrons. 11 is odd electron. So therefore, if you go to the structure of nitric oxide, I can create 2 covalent bonds like this, and 3 electrons I can place it in between, and 2 electrons I can place it over here like this. So this is 3 electron, 2 centered, 3 centered. You can just take here 2 covalent bonds, means 4 electrons are there, 5, 6, 7, 8, 9, 10, 11. this is 3 electron, 2 centered odd electron molecule. So this is the structural aspect of the nitric oxide. Now going back to, that is N2O, nitrous oxide. If you go for N2O, nitrous oxide, you can prepare nitrous oxide by taking ammonium nitrate. Ammonium nitrate solid, upon heating, it undergoes decomposition. It gives, that is nitrogen N2O plus H2O. If you take, there are 4 hydrogens, so take 2 over here, and yes, there are 3 oxygens and 2 nitrogens. Yes, it has already, we already got the that is nitrous oxide, and here the oxidation state. So what is interesting here is, if you go for ammonium nitrate, what is the oxidation state of ammonium nitrate means you have to split this into 2 parts. One is the ammonium ion, and we are going to get one nitrate ion, ammonium nitrate. So what is the oxidation state of nitrogen in both these cases means, in nitrogen, in the ammonium cation, the ammonium oxidation state is -3, and in nitrate ion, the nitrogen oxidation state is +5. So that means it has both the oxidation states, one is -3 and +5. So 2 types of oxidation states are there. So therefore this is one point which you have to keep it in your mind. And if you go to the structure of the nitrous oxide, yes, it has 2 nitrogens and 1 oxygen. So the best thing what we can do is, you can create 2 double bonds between both the nitrogens, and if you take the middle nitrogen, because it contains 5 valence electrons, so one of the electron from the middle nitrogen is going to be transferred to the other oxygen side. So suppose if I am going to take here, out of 5 valence electrons, nitrogen has only engaged itself in the 2 covalent bonds with only 2 valence electrons. Rest of the 2 valence electrons are like that only. So right now I think oxygen is showing the octet because 2 lone pairs are there and 2 covalent bonds are there. So therefore oxygen is trying to show the octet configuration or octet stability. Even nitrogen also, it is able to show the octet stability, but it has 1 electron in surplus. So if it is having 1 electron in surplus, this electron is being transferred to this nitrogen, and it acquires the stability. So therefore I can say that a kind of resonance stabilization occurs here. You find here one nitrogen acquiring positive charge, and here one nitrogen tries to acquire negative charge. So therefore all the 3 atoms in the nitrogen, they are able to acquire the stability. So for the first nitrogen with 2 covalent bonds and 2 non-bonding lone pair of electrons, octet stability, middle nitrogen octet stability, and the last oxygen also, it is able to show the octet stability with the 2 lone pairs of electrons and 2 covalent bonds, all are able to satisfy the octet stability. So that therefore the overall molecule is able to acquire the octet stability. So if you go to the next part of the discussion, that is NO2, go to the third case, that is NO2. If you take, it can be prepared by decomposition of lead nitrate. When you heat lead nitrate, you get lead monoxide plus nitrogen dioxide plus oxygen gas. You can take nitrogen dioxide gas, and this is a solid. Of course you need to balance the equation. Then of course if you are going to take 2 over here and 2 over here, and I think 2 2s 4, 2 2s are 4 nitrogens, so take 4 over here, 8 plus 2 10, 10 plus 2 12. Yes, everything is balanced here. So in this way we can prepare nitrogen dioxide, and take this nitrogen dioxide. It contains this nitrogen dioxide, it contains 1 nitrogen. It has 1 nitrogen and it has 5 valence electrons, and there are 2 oxygens. 1 nitrogen, it has 1 nitrogen which it has 5 valence electrons, and it has 2 oxygens, wherein which it has, each oxygen has 6 valence electrons, 6 to 12 electrons are there. So therefore you can take this whole as 17 electrons. 17 is an odd electron. So based on this, if you go to the structure of the nitrogen dioxide, yes, you can give 2 different types of structures. Yes, yeah, that is like if you go for nitrogen dioxide, double bond oxygen, and you can take 1 single bond oxygen, and here oxygen has 6 valence electrons, out of which 2 are involved in the formation of covalent bond, and that is oxygen has 6 valence electrons, in which 2 are involved in the covalent bond formation, and the 2 lone pairs are visible like that only. Here if you go for nitrogen also, we have 3 covalent bonds and we have 2 electrons, and so 1 out of 6 valence electrons, 5 valence electrons are visible for the oxygen. So but right now the oxygen is not stable, so the best thing what the nitrogen can do is it can donate 1 electron. It can donate 1 electron, that is donated electron. It can donate 1 electron. When it is donating, the oxygen is going to become stable, but still it has 1 electron, 1 odd electron left on the nitrogen to become stable. So that means here what is happening here is, like left side we have a double bond, right side we have a negative charge, and here here this oxygen becomes that is here this oxygen, any one of the nitrogen or oxygen, it's going to become unstable in the Lewis electron dot structure. So I can say that here nitrogen can acquire positive charge and oxygen can acquire negative charge. This is one structure you can give, or else you can create one coordinate covalent bond between one of the oxygen using 2 covalent bonds. So therefore the best thing what I can do here is, then you can use 2 lone pair of electrons, and here you can contribute altogether 1 pair of electron to the oxygen. So the 2 oxygens are outright stable, but still you can find that the nitrogen has 1 odd electron over it. So therefore this odd electron represents in its structure, this is the odd electron. So because of this odd electron, you can find that this nitrogen dioxide, it immediately undergoes dimerization and it forms, that is dinitrogen tetroxide, which is a solid. This is the dimerization. This is the dimerization which is taking place in the case of nitrogen dioxide. And one more thing, what is the important point you have to gather here is, if you go for nitrogen dioxide and when you are going to hydrolyze it, I think it's going to give us that is HNO2 plus HNO3. So you take 2 molecules of nitrogen dioxide. So what is the oxygen state of nitrogen in nitrogen dioxide? Here the oxygen state of nitrogen is, that is plus 4 of nitrogen, and here in nitrous acid the nitrogen is plus 3, and here the nitrogen is plus 5 oxidation state. So that means this nitrogen dioxide, therefore you can come to one conclusion that it's a mixed anhydride. It is a mixed anhydride of the nitrous acid as well as nitric acid, because in nitrous acid we have plus 3 oxidation state, and in nitric acid it is plus 5 oxidation state. The nitrogen dioxide is having an oxidation state of plus 4, so the plus 4 oxidation state is in between the plus 3 and plus 5. That's why we can regard the nitrogen dioxide as an mixed anhydride. And so therefore we have completed the nitric oxide, nitrous oxide, nitrogen dioxide, and I think now we have to go for the nitrogen sesquioxide and nitrogen pentoxide. And this nitrogen sesquioxide is bluish, you can take this as bluish solid. We can consider this as bluish solid in the case of the oxide, and nitrogen pentoxide is the last oxide. So let us go to the next part of the oxide, that is nitrogen trioxide. This is N2O3. I think this is the 4th case which we are studying here, N2O3. So this is nitrogen sesquioxide. This is dinitrogen sesquioxide. It is a bluish solid and can be acidic, and it's an anhydride. It is an anhydride of nitrous acid. That's because if you take N2O3 and when you are trying to hydrolyze the dinitrogen trioxide, you are going to get HNO2. That is, here this is going to be plus 3, and here also it is going to be plus 3 oxygen state for both the nitrogens, that is nitrous acid and dinitrogen trioxide. So it's an anhydride, direct anhydride of the nitrous acid. And if you want to prepare the preparation, if you go for the preparation, take the equimolar mixture of that is NO and NO2 gas, you get N2O3 solid at around 250 Kelvin you can take here. This is the best method. And if you go to the structural aspects, structure, Lewis electron dot structure, if you apply, we have 2 nitrogens and 3 oxygens. So if you have 2 nitrogens and 3 oxygens, each nitrogen 5 valence electrons and each oxygen number of valence electrons are 6. So 6 into 3 we get 18 electrons for 3 oxygens, and we have 2 nitrogens, so 5 into 2 which is going to become 10 electrons. So 10 electrons plus 18 electrons, total you have to get 28 electrons in the Lewis electron dot structure. When you go for the Lewis electron dot structure, including the lone pair of electrons and the covalent bonds or coordinate covalent bonds what you take in the structure, that structure should match 28 electrons, and all the atoms should have the octet stability when you are going to take a structure for this particular oxide, that is dinitrogen trioxide, that is sesquioxide. So because it contains an odd number of oxygens, you can straight away just take one nitrogen to nitrogen linkage we can take straight away, and you can create one coordinate covalent bond, the covalent double bond and coordinate covalent bond. So the nitrogen has become the pentavalent because one coordinate covalent bond can be termed as 2 covalent bonds. And here also you can just take on one side, you can just take it over here, one covalent bond, and 3 oxygens have been completed. So definitely one lone pair exists in the oxygen, and so therefore you are finding that the rest of the lone pairs on the oxygens can be highlighted accordingly. So here also oxygen, because it is taking up one coordinate covalent bond, 3 lone pairs have to be highlighted, and here this is the structure which is possible for the dinitrogen trioxide. Or you can just take the 2 covalent bonds for oxygen with the lone pair of electron, then here one single covalent bond, again a double bond, again a double bond. So here you can take the lone pair of electrons, and you can see if you count the number of unpaired electrons, if you count the number of lone pair of electrons, you have total number of lone pair electrons in this structure. If you take in particular, if you take 1 2 3 4 1 2 3 4 5 6 7 to 14 electrons are there, 14 electrons, and covalent bonds 14, and we have 16 18 20 22 24 26 28. So total number of electrons are matching in the structure, and all the atoms are acquiring the octet stability. So therefore the structure of N2O5, the Lewis electron dot structure of N2O3, is justified because all the atoms in the structure are getting stable. So the last oxide, that is nitrogen pentoxide, dinitrogen pentoxide. If you go to that is dinitrogen pentoxide, if you are taking here the dinitrogen pentoxide, if you go to dinitrogen pentoxide or nitrogen pentoxide, it is highly acidic oxide. It is highly acidic oxide. The reason is because in nitrogen pentoxide, nitrogen oxidation state is +5. That is one reason. Then second thing is, if you want to prepare nitrogen pentoxide, yes, you can prepare it from directly nitric acid itself. Nitric acid, when it is treated with the phosphorus pentoxide, which is acting as a dehydrating agent, so you are going to get N2O5, no doubt about it, but at the same time it is going to give metaphosphoric acid. So if it is giving metaphosphoric acid, I suppose that if you are going to take here, phosphorus pentoxide is acting as a dehydrating agent. So dehydrating agent. So if you have a careful look at the equation, you understand that here, because there is no change in the oxidation state of phosphorus as such. If you go for phosphorus pentoxide, here in the phosphorus pentoxide, the phosphorus is having +5 oxidation state, and here also the phosphorus is having +5 oxidation state, and here in the nitrogen you have +5 oxidation state, and here also in the dinitrogen pentoxide also phosphorus is having +5 oxidation state only. So that means as such there is no change in the oxidation state of either nitrogen or phosphorus. So in both the cases you are finding that the nitrogen and phosphorus oxidation state remains one and the same. So then if that is the case, then what exactly is happening in that reaction? So phosphorus pentoxide is just acting as a dehydrating agent. It is trying to remove the water, it is trying to remove the water content from the, basically it's an oxy acid, it contains certain water in it, so it is removing the water in the form of metaphosphoric acid, and here the phosphorus pentoxide is getting converted from oxide to oxy acid. Pentoxide of phosphorus is converting itself from oxide to oxy acid, and nitric acid of nitrogen is converting from oxy acid nature to the oxide. So it is a reverse properties of the oxide of phosphorus and oxyacid of nitrogen. So oxyacid of nitrogen is converted to oxide and the oxide of phosphorus is converted to oxyacid. That's why this reaction has that kind of tendency. That's why it's very interesting to note like that. Fine. So if that is the case, now if you go to the structural aspects, if you go to the structure of N2O5 using the Lewis electron dot structure of N2O5, if you take, yes, 5 is an odd number, so higher odd number in the given structure can create nitrogen oxygen nitrogen linkage. So here oxygen is having a lone pair of electron. Yes, you can create a double bond oxygen with 2 lone pair of electrons. Here also you can create a double bond of oxygen with 2 lone pair of electrons. You can either create a coordinate covalent bond or you can just create a coordinate covalent bond. Both mean one and the same here. So I am creating a coordinate covalent bond. So the oxygen is stable, everything is stable, and you are finding that this is the structure of nitrogen pentoxide. And interestingly, again, nitrogen pentoxide, when you are subjecting it to hydrolysis, it gives back the nitric acid. Here the oxygen state of nitrogen pentoxide is +5. Here also the nitrogen oxygen state is +5. So therefore I can say that this is anhydride. It is an anhydride of nitric acid, because both has the same oxidation state. So the next part of the discussion here is preparation and properties of nitrogen. Preparation and properties of nitrogen. This nitrogen is a colorless gas. It has low solubility in water. It has isotopic forms, isotopic in nature. It has 2 isotopic natures, 7 nitrogen 14 and 7 nitrogen 15 it has. And this nitrogen, if you take, it has very low melting point and boiling point. And you can prepare this nitrogen, you can prepare this pure nitrogen. Pure nitrogen can be obtained in 2 methods. One is you can subject it to fractional distillation of the liquid air. When it is subjected, you find that here you get 2 distillates, that is liquid nitrogen and liquid oxygen. So this liquid oxygen is distilled off and finally you are going to get liquid nitrogen. Apart from this, you can prepare the pure nitrogen from heating barium azide. So barium azide, if you take N3H, means you can take BaN3 taken twice. This is barium azide. Barium azide, if you take, you can just heat this barium azide, you get nitrogen gas, pure nitrogen gas, and you get barium solid. Balance the equation, take 3 over here, and yes, it's already balanced. Then apart from this laboratory preparation, if you take in lab method, you can take ammonium chloride. You can take ammonium chloride and you can treat it with the sodium nitrite, I suppose. Then you are going to get nitrogen plus sodium chloride, sodium chloride. Then I think we can take that is HNO2. If I am going to take HNO2, if you take, so here ammonium chloride, when it is reacting with sodium nitrite, ammonium chloride aqueous, sodium nitrite aqueous, nitrogen gas, sodium chloride aqueous, and you can take water as the byproduct. This is liquid. Then you can also take that is ammonium dichromate. Through the ammonium dichromate also, when you heat ammonium dichromate strongly, also you can get nitrogen, that is N2 plus Cr2O3 chromic oxide plus, I think you can take H2O. So balance the equation. We have 2 nitrogens and 8 hydrogens, so that's why we have 2 chromiums and we have 8 hydrogens. So suppose if I am going to take 4 over here, yes, automatically the reaction is going to get balanced and you get, that is nitrogen gas. So here we could find one more method, one last method what we can prepare for nitrogen is like we can take ammonium nitrite. Ammonium nitrite, upon strong heating, it is going to give that is nitrogen gas plus H2O. This is the simplest method where you can adopt liquid, and this is solid. So when you heat it, you get nitrogen gas plus water. So these are the three important methods where you can prepare nitrogen. And if you go to the general properties, if you are going for the properties, chemical properties of nitrogen, this nitrogen, because of its this nitrogen can readily react with metals as well as non-metals. That is, first one is action of metals. If you go for action of metals, yes, it can. With lithium, it forms lithium nitride, and with magnesium, it forms magnesium nitride. And sometimes it can also form with the calcium in the presence of calcium carbide. Suppose calcium carbide, if it reacts with nitrogen, it forms calcium cyanamide plus carbon. This is calcium carbide, CaC2 is the calcium carbide. It reacts with nitrogen, it forms calcium cyanamide plus carbon. This is magnesium nitride, and this is lithium nitride. So here this calcium cyanamide plus carbon, this forms a nitroleum mixture, and here this carbon is simply called as, that is, graphite, So this is action of metals. And when you go for action of non-metals, plenty of reactions are possible. Action of non-metals, that is, action of non-metals, if you take, it can react with the hydrogen into gas, reacts with hydrogen gas, reversible reaction, it forms 2 moles of ammonia gas. This is manufacture of ammonia through Haber's process. Under the optimum conditions of pressure and temperature, reaction is exothermic, we get 2 moles of ammonia. Then like this, you can go for nitrogen readily reacts with oxygen at certain temperature, it can give nitric oxide gas. Then likewise, nitrogen can react with other non-metals also, like oxygen and hydrogen, and it can give different compounds.